Okay, we started the second and the last part of this afternoon. We have a few talks given by the students of the 26th cycle. The first one is Luca Carafoli. Okay. Okay, thank you.
Good afternoon, I am Luca Carafoli, and during my talk I will present my research activity entitled Data Management in a Modern Intelligent Transportation System. My research activity is related to the Pegasus project, which aims to build an intelligent transportation system to improve the safety. Okay. To improve the safety in urban mobilities. This project is funded by Industria 2015 program, and it was many partners. In the Pegasus scenario, vehicles can communicate each other through a Wi-Fi connection, and with a centralized control center through GPRS interface. Control center is the core of the system, and it receives raw data from vehicles, and it sends to them useful information as weather and traffic condition, or point of interest, and so on. All data coming from vehicles are stored in the control center for online and offline analysis. In this scenario, in this year, I've been working on two project research fields on data stream management to improve the state-of-art data stream paradigms to meet the project requirements, and on data reduction techniques to reduce the communication cost between vehicles and control center to improve the efficiency of the system. In data management, in this context, poses three main challenges. The first is store, access, and manipulate in real time a large amount of geolocated stream items. The second is promptly answer user requests, and the third is retain stream item beyond the real-time processing. Sorry. And furthermore, the control center should be able to manage both continuous and one-time query to support the Pegasus data request. For example, show me the best path given the current traffic situation and weather condition is a typical Pegasus data request that involves both continuous query. An example, every minute give me the last average speed per segment, and one-time queries. The one-time queries, the standard SQL query, for example, give me the today weather condition. To meet this requirement, we cannot adopt the traditional data stream management system because it doesn't retain stream item beyond the real-time processing. The data flow in the systems, and they are not stored. And it is not able to integrate real-time data with other sources. At the same time, DBMS paradigms too isn't applicable because it can manage streams. It is inefficient in case of frequent updates, and it adopts a store first query later approach. To overcome this limitation, we introduce a new kind of relational table, streaming table. Streaming table is a new kind of DBMS table where streaming data enters and remains stored for a long period, ideally forever. It fits into the relational model and into the DBMS architecture and enables DBMS to manage a stream. We extend the DBMS with the streaming table by introducing developing storage methods that span both main and secondary memory, proposing and developing two novel types of index, and extending the standard SQL language to support continuous query. Furthermore, we do a comprehensive experimental evaluation of the proposed implementation. We test our system with the popular linear road benchmark, a reference benchmark for data stream system. Furthermore, we extend the benchmark workload by adding 100 one-time queries every minute. We did many tests on the system and a deeply analysis of the obtained results. This graph shows an overview of the obtained result, and it shows the response time. It shows that the response time is ever less than 1 second in spite of the tuple load increasing during the test. In another test, we did a comparison with the other paradigms, in particular with NoSQL database, Cassandra 1.1, and standard DBMS. This graph showed that in a situation of high insert rate, with the NoSQL database and the standard database worsen their performance during the time. Instead, our system keep the time response stable during all the tests, in general forever. The second field is data reduction techniques. Data reduction techniques are vehicle-side techniques that aim at reducing the amount of data update communication. We investigate a set of independent techniques, and we classify them in two categories. The first is independent techniques, where the vehicle decides when to issue update to the server, for example, every 5 seconds, every 100 meters, or at the end of a map segment, or in a crossroad. And the second is an information need techniques, where the vehicle decides when to transmit on the basis of specific information made available by the control center. To evaluate the effectiveness of these techniques, we test them by means of simulation performed on 4 different scenarios. The first is Bologna, a portion of the city center of Bologna, a portion of a north central junction of Roma, and a portion of a multi-way junction with a toll pay station in Camden, this toll plaza, and a crossroad in Beijing, very intense and congested, and with many kinds of vehicles. The table show that Bologna and Beijing are slow urban scenarios, differently from Toll Plaza and Roma, that are faster than Bologna and Beijing, and that Beijing has many frequent and very long stops, and in Bologna and Roma, stops are short and frequent. We consider the communication cost side by side the average error produced by the control center in 2 different data Pegasus data requests. Okay, from performance test, we infer that there is no techniques that performs better than the others in all scenarios, and that the simple and general techniques performs on average better than the more complex techniques. In the future, we'll work on dynamic data reduction techniques based on control center workloads, in approaches for online data summarization and preservation, and on query processing with aggregate and missing values. Thank you for your attention.
So thanks for your talk. Questions? Okay, we go to, we proceed with the next talk. Miss Daria Coppi actually is in the United Kingdom. I don't know if there is anybody giving a presentation. I don't remember what she told me. Okay, actually we have Daria Coppi and then Matteo Fiorani. Matteo Fiorani is not here, and he gave us his file, but his presentation file, but the audio does not work. So we proceed with Michele Fornaciari, the next one.
Adesso va? Ottimo.